Yeah, thanks. Okay, let's get started. Again, next week we don't have lectures, okay, and we will pick up during the week. Any questions from previous class? Yes.
In the last lectures, we have learned about collecting theory.
Yes.
What is different from the independent theory of the collecting theory and spatial linear group?
The spatial linear group is that? Scalar is a d 0,0. So yes, so that's the scalar field. So if that's all you have, then you know what to do with it. So now we are introducing higher spin state in the theory, including fermion and vector soon. So and once we have that, then we can construct a theory that now looks like describing parts of this world, which is quantum electrodynamics. Right, so the goal is to get there as soon as possible. And then well, we're going to study a little bit about that, but then yes, then we'll study deeper aspect of quantum. Any other questions? Okay, so last time, I guess I stopped while I was discussing construction of a Lorentz tensor vector scalar out of U, right, with U object. So today we will finish that up, and we will construct the Lagrangian. We will study equations of motion, and then we will learn some physics out of it. So that's, and then we will move on to Dirac, not just the file. Hopefully, this is not too dark for you. Is it or not? This is okay?
Very small.
Okay.
Not that right. Not that right.
Thank you.
That's right.
Very good. Thanks so much. So we had a light on, right, last time. It was not just me that had a weird feeling. Right? Okay, cool. So last time we talked about this U plus U minus object. And then the question is, what are the possible Lorentz tensors we can construct out of this object? And I believe one thing that we can construct is, for instance, for U plus, we can construct probably I call the mu, then U dagger, sigma bar mu, U plus, where sigma bar mu is identity 2 by 2 and minus Pauli matrices. Okay, so I think I finished that part last time, yes? And then for U minus, we can construct a W in a very similar fashion. So now instead of sigma bar, we have a sigma just, and in this case, sigma is 1, 2 by 2 matrix, again, plus Pauli matrices. Okay, then we can also construct, these are the Lorentz vectors we can construct. We check why this is the correct sign in such a way that this combination as a four-component object transform in a correct way under the boost as well as the rotations, right? So then, did I talk about Lorentz scalar last time or not? Didn't I? I didn't? Okay. So then we can also construct the Lorentz scalars. So for instance, if I have this, again, since SL2C can be thought of as 2 copies of SU2, right? So then we have one object transforming under one of those SU2, and there's another object which is transforming under a second SU2 vector. So if I give in that structure alpha, alpha, alpha dot, each of them runs 1 and 2, again under the SU2 indices, I can construct Lorentz scalar by constructing simply SU2 scalar by contracting like this. So, and then here too, I will explain in a minute the minimal amount. Doing everything is like opening the Pandora's box. So I can open it irresponsibly and then let you figure out the rest of the convention. Anyways, I'm not gonna open. Well, I might open. So in this notation, yes, there is this contraction for the left. So these are the left-handed, which you, as you will see, these are the right-handed. There's an A, which I will explain why there's an A. And then there's a contraction that way, and there's a contraction that way. Now, so in this notation, roughly speaking, you can think of this as for right-handed spinner. I told you that these are two component object that transforming under the SL2C as its S equal to half representation. So the notation is that for left-handed guy, once again I will explain why. Upper index is like row vector. And for that guy, lower index is behaving like column vector. So you're just computing matrix multiplication, which is now invariant. For right-handed guy, the meaning of that gets reversed, right? So lower index is like a row vector, and the upper index is like column vector. If I say, why would you do that? Right? Why would you do that? Good question. And there's a whole literature about all these conventions. Okay, welcome to the physics world. So anyway, so for now, let's just remember that. And anyway, my point is that you can also construct these Lorentz scalars. Schematically, I'm just gonna write this as this schematically again. This. Okay. Now we can also construct tensor. So now we can also construct two index and this metric tensor. So how would I do that? So one can you can guess this as follows. You can ask yourself, what do you have as an ingredient to construct those objects? Well, you have U's, you have sigmas. That's all, right? So this is all you have. Now the question is, out of this ingredient, how would you put them together to construct non-trivial, nice behaving Lorentz tensors? That's the question here, right? And I just explained to you these notations. Now, if you look at this expression, for instance, even though I introduced secretly this thing, now I can put the notations back. So let's figure out what is the index structure of this guy. So U, this should be row vector, column vector, and then 2 by 2, right? That's the structure. So column of the left-handed guy has index down, and then row of row of right-handed guy. Again, if I dagger, I switch from the left-handed to the right, left-handed to the right-handed, right? Remember that? If I have a dagger, I'm going from F0, 2. We talked about this. Complex conjugation switch is how this can transform. And then row vector of that guy had index down, so alpha dot, which means that this guy will have index structure of alpha dot alpha. We can do the same thing here. So now I'm talking about the right-handed guy. That for that column vector has index up, and therefore this guy will have index down. So just beta. Then this thing, beta, because this is row vector of the left-handed. This guy has an index structure of a down beta alpha dot. Okay, so far so good, or you're already lost. I told you. This is not my fault. Yes.
So does that the left-handed just order must be the same for the same for everything? I mean you raise the left-handed indices up in the first.
Where are you? Are you here?
Yes, but you also so
because I told you that the way it gets contracted for the left-handed guy is that way, that the way right-handed indices with dot gets contracted that way. So you see, correctly left-handed, correctly right-handed, correctly right-handed, correctly left-handed.
so that must be obeyed every time.
Most of the time.
Okay, I see.
Okay, I can explain what do I mean by that. Let's see. I mean, if I have the time, actually, I can explain a little bit more about that. So either yes. You
Can you continue?
Yes, sir. Let me continue. Yes, if I have time, probably by the end of the this part of the discussion, I can also give you the say 20-30 minutes of summary or what am I talking about here, right? So what's the index, what's the combination, how to think about all of that? Yes, you had a question.
I think I'm a little bit skipping something, but is U plus and U minus plus one number?
Good. So at this point, you wouldn't know, but eventually, yes. So at this point, I already only told you that this is a two-component object. But then we will learn that this must be anti-commuting two-component object. By which I mean, if you have a product of two and you switch the order, you have to pick up the minus sign.
The reason why I was asking about that is because the row vector and column vector is not important when we write just the component alpha. So
Sure.
yeah, so I thought that
Well, but yeah, without this, I was writing, if you like, vector notation.
yeah. Okay.
I'm putting the indices back to explain that part, how to construct the two index antisymmetric. So again, since I have only U's and sigmas, I already saturated only using U and then U together with one factor of sigma. So next thing we can try, because I want to see the two Lorentz index. The Lorentz index only comes from the sigmas. So now I have to use the two sigmas. Is that clear, the logic? So what will be, so if I have a sigma nu, for instance, I can put U plus here, according to this. But then I have to have something like this, either bar or on bar. Let's figure that out. But my claim is that you have to have without a bar to be able to contract with the U, only U, without a U dagger. So I'm saying this is a consistent object. You can again keep track of all the indices as I explained here, that this contract all the SU2 indices properly. Okay, so it's not a two bars here, but it should be that way. And you can quickly see why that's the right thing. Okay. Well, you already see if you had only two sigma bars, already if you put sigma bar here, there's no way to contract indices, right? But if you put sigma followed by sigma bar, see already there's alpha that can be contracted. Okay, so let's consider this object. So two U, not U dagger, and then two sigmas this way. Now you learn that you can now decompose immediately, like F antisymmetrized version plus like so. Okay, so obviously this guy will capture two index antisymmetric part. This guy will capture the symmetric part. Let's see. Now, so by the way, there is a sigma identity which will be part of the homework. Is that this is equal to 2 times metric tensor, because these are symmetric mu and nu, and then this will be identity in two-dimensional spinor space. Okay, so that is the identity that you will have a chance to show. So now let's look at one by one. So first, obviously, the first term is what we wanted to achieve. So we wanted to have constructed something out of the U and sigmas, which is antisymmetric in Lorentz indices. Okay, that's the correct thing. The second thing, on the other hand, let's look at only the second thing. Therefore, so that is basically eta mu nu, which is metric, and then this contraction with identity. So which we have seen already. So this is nothing but Lorentz scalar I talked about. Okay.
Okay. Do you mean by so I'm confused if you have two U plus at the same time? Is it legal?
If I have two U's.
I confused, sorry.
Okay,
Yeah.
good. Okay, is that clear?
Yeah.
So then the second thing, yes, it is a correct a symmetric two tensor object, but actually secretly it is actually just Lorentz scalar part, right? Because there's a non-trivial symmetric tensor. It is only the symmetric dependence that give you symmetric two tensor. Okay, therefore we at this level we saturated that out of this guy we can construct a vector, scalar, and then two tensor, antisymmetric two tensor. You can keep going if you want, but anyway, this is how things work. Now, having understood this much, let's now start constructing a Lagrangian out of this object. Any questions so far? Okay, so now I want to construct Lagrangian out of this your field, Fermionic field. So there are a couple of criteria that Coleman listed. So let me list them so that you can also compare and see what he does in the book. I mean, I'm going to follow mostly, but I will provide you some of my opinions. Not just my opinions, but facts. So criteria number one, they should be Lorentz scalar for obvious reason. Because if you want to construct a Lorentz invariant field theory, so that's clear. Second criteria, so this has internal symmetry. Example is something like some U1 symmetry acting on U fields. Okay, so he wants to construct Lagrangian which respect, for instance, this U1 internal symmetry. This is not necessary, but sometimes useful to think about. So I will give you a construction which does satisfy this and also doesn't satisfy it. Okay, so we can think about them both. And then Lagrangian is a bilinear in field using two daggers, because this will give you, if it is bilinear, give you linear equations of motion. Why that's useful? Bilinear equations of motion can be solved. Okay, this is a linear equation. You can solve it. If you understand the equations solution to the equations of motion, then you can quantize it, and then you can start adding extra small perturbative interactions. Then you can take this as a base of the quantum field theory, and then you can add extra perturbative interactions. So this is good to study. Also, generically, if you have a quadratic theory that's solvable in a sense, basically you can understand everything about it. It's good to study. And then at this level, we're going to consider Lagrangian that does not have more than two derivatives. Okay. Again, just like the criteria 2, this is not an absolute necessary criteria to add. But again, it is useful to study no derivative, one derivative, two derivatives, and so on and so forth. And in fact, in the literature, there is a study that what happens if I have very high derivative fields, whether there is any issue with that. And often you will encounter problem if you have a lot of derivatives. Okay, those are like unitary and causality constraints. Then finally, he considers the action, which is space-time integral of Lagrangian, is real. And this is directly related to the fact that you want to get the Hermitian Hamiltonian eventually. So this one is also clear. This is a clear, and then again, I will go through a similar construction, and then I will also show something that doesn't satisfy, for instance. Okay, so now therefore let's first start writing down possible candidates that can possibly terms appear in the Lagrangian. Okay, who are the possible terms appearing in the Lagrangian? Well, so let's first follow this Lorentz invariant, Lorentz scalar. So which I know the building blocks, right? So Lagrangian therefore possibly contain terms like Lorentz vector. Well, obviously Lorentz vector alone cannot appear, so possibly this can have, I don't know, b mu. Let's first talk about the W plus only, or derivative b mu, which are all nicely converted to Lorentz scalar. And you can keep going, but also I can add this. Once again, I'm focusing on only the U plus theory for now. Okay. And if I want to use this antisymmetric tensor, then just dagger. This doesn't work because this is antisymmetric, this is symmetric, so this doesn't work. Okay, so I'm just writing so that you can understand that. But instead, we can try to consider something like that, by which I mean you write down another one with two indices down. Okay, so you might be able to contract it properly, and so on and so forth. Okay, so you see some systematics. Now, if I demand that my theory is a bilinear in field, obviously this is out because B already has a two U's, right? One U dagger, right? So this is a coordinating U. This is good. This is good. And this is out, and this is also bad because it has also four U's in it. Okay, so already this one selection only the one, like two terms allowed. So forth. Okay, so let's try to write that down. Therefore. So that looks like up to some constant, which I don't know yet. U dagger sigma bar mu derivative U. Okay, so here's one term. Then another term, let me call D U1 squared. Good so far? Good. Now, okay, we will eventually fix all these parameters and understand the physical meaning of that. Now, let's already talk about. So therefore, we automatically satisfy this criteria. Now, we will check this soon. Let's first talk about the C2. So this, for instance, does satisfy the fact that this guy may have internal symmetry. Meaning, if you do make some sort of U1 transformation, because one is U, the other is U dagger, they cancel out, right? So this checks out the C2. But this, if you make U1 transformation, obviously this is not invariant. So C2 is violated, for instance. Okay. And why am I only talking about the U1, for instance? Well, that's the only thing I can talk about now, because there's only one field, just like the scalar field. If I had identical n-component field, I can talk about UN or ON and stuff like that, right? But I have only single field. And the maximal symmetry I can imagine is just U1. There? That symmetry could be Glover symmetry, or could be, as we will talk about, KAIST symmetry. But don't worry about that word. Okay? Anyway, this respect is doesn't respect. Okay, so now let's impose C5. So therefore, if you actually impose C2, this is it, right? That's all you have. Okay, but let's keep it for now. So let's impose on C5. So in order to do that, we have to understand the complex conjugation of this thing, and complex conjugation or dagger. You can check that it's this. This basically uses, reverse as if it is a Hermitian conjugation. Just replace it. Okay, or okay, good.
Oh, Professor?
Yes,
It is just complex conjugate, not Hermitian conjugate.
but it is true. Okay, and explaining why it is part of that box that I'm trying not to open, but open in front of everybody. That's what I'm saying. But you will have to open. That's the point. But then the answer is yes. This is the. I will try to make the homework so that you can walk through the calculation and check. Any other questions? Okay, so now how do we know? So for a second, let's drop this part for a second. Let's make sure how this can be, Hermitian or real. So, but for now, I can first do one thing. So we can always do make what is known as a field redefinition, such that U gets scaled out by square root of that thing, C, then the Lagrangian will go to up to plus minus sign now, because I don't know how to fix the sign yet. In terms of U field, my action or Lagrangian will have this form. And then D will be shifted too. So let me just then say that I have a new parameter D after rescaling. You know how D tilde is related to the D because you have to basically scale like this. Okay, so you know what I'm talking about. Or not? Is that clear what I'm doing? So I started out here, and in principle, there is a sign ambiguity which I don't know how to fix yet at classical level. So I just made a field redefinition by rescaling the field by this much. So the coefficient in front of that is just the 1, but I don't know which one is which sign yet, which I will have to fix. And if I do that, then new parameter appears is, if you like, in terms of all the parameter is this. That's what I'm saying. Okay. Now, again, I'm going back to C5 and checking the reality of the action. So how do I do that? So I just told you that in the complex conjugation of this term is that. And then the task is to see whether this is the same as that or not, right? If this, which is complex conjugation, is the same as that, then I know it's a real action or real Lagrangian. If it's not, I have to worry about it. Okay? So now, in order to check that, note the following. So if I take this object without a derivative, and then if I look at the derivative by chain rule, I get okay, so for obvious reasons. There's a plus sign here. Okay, so I guess I have somehow in my mind there's a conservation plus. Okay, you know what I mean. And if I consider my space and time, M4, doesn't have any boundary, so I can drop the surface down. Okay, so therefore derivative of something and just drop it. Then this shows that this, which is nothing but this, is actually a minus of that thing, original thing. Okay, so just to be totally clear, let me write. It's not equal to itself, actually minus of it. So naively, this Lagrangian is not real because A complex conjugation is that, and I showed that is equal to minus this thing. Okay, so in order to get a real action according to this C5, therefore I can should do the following. So it's very easy because now I just define my Lagrangian to be plus minus times I times plus d tilde, which may okay. Yes. So this part of the sign, which we will fix eventually when we quantize this theory, is the action for the bifermion. In this case, I'm taking one single bifermion. Okay, what about that? So this obviously is not real, right? Because if you have U, your star is not U. That's whole point, right? Why this the representation of law is not purely invariant, that's one of those. So obviously, in order to make a full Lagrangian invariant, we have to put complex conjugate of the last one. Okay. So then you can do the same thing. Now, if I do the same thing with the U minus, you will basically get almost the same answer. Now, instead of U, sigma bar, you get the sigma. And then in principle, if I say plus, you can add the mass. So that's the Now, at this point, let me state one thing and then move on. So, as we'll see now, this will take the interpretation of a mass term. Okay, because physically there is a propagation of a u eventually, and a single point it fills the insertion of this d tilde keep going. So it will behave like mass, which I will drive now momentarily. So let me call that a mass, therefore. But this mass doesn't respect if theory had any either internal U1 global symmetry, as we talked about, right? Because that thing is not invariant under some U1 transformation. So either if you had a global symmetry of U1, then such a term is explicitly violating those U1 global symmetry. The example existing in the literature, I'm just telling you a word so that you have a chance to hear that, and somebody hear again. So this is the example of what's known as the Majorana mass. A mass that is constructed only out of a single bifermion, which doesn't respect any sort of U1 or global symmetry or gauge symmetry. So such a term is allowed only if this is transforming under real representation of the global symmetry or gauge symmetry. Because this, if you complex conjugate, sorry, let me say that again, there's a Majorana mass, but it is allowed only by the Lorentz invariance. But if you had extra global symmetry, sometimes such a thing is not allowed. And it is allowed only if that field transforming under real representation of either global or gauge symmetry. But you haven't heard anything about gauge yet, so don't worry about it. So now let's actually see, why that's the mass term. So in order to see that, what do? We derive equations of motion. So let's derive equations of motion right away. Okay, so again, we're going to study plot side. Let's study equation of motion for U plus. One is easy, the other is not. Well, the other is not also easy. So in order to do that, let me explicitly write down this complex conjugation. I'm going to look at the equation of motion for U plus dagger. This is the star, then U dagger square. So that's the complex conjugation of that thing. So I'm going to look at the equation of motion for U plus dagger, because that's easy to do it, because this doesn't have any derivative terms. I'm just going to look at the functional derivative, and that should give me plus okay, so that's the answer. Okay, so far so good. Are you lost? Yes.
Shouldn't it be true at the second term? Because you have two U plus.
Very good. So that okay, thanks. Usually therefore in the literature, whenever you see Majorana mass, you will see over 2. So yes, if I didn't put this, I should have 2 here. Oh, that's why some of you like, oh, something wrong.
여기서 마이너스에서 하는 걸 정확하게 어떻게 얘기해요? 지금 제가 다루고 있는 게 매스기사 바이올린 쪽 아니
Good. So well,
그러니까 저 매스가 들어온다 이거 어떻게 그러니까 저에서 어떻게 해야 되는지 궁금해요.
okay. Let me explain in 2 different ways. A, we took bifermion as a building block for my QLT. And in order to construct Lorentz invariant Lagrangian, we say, what are all possible building blocks? So we constructed the Lorentz scalar, Lorentz vector, Lorentz tension, and so on and so forth. And then turns out, just based on Lorentz invariance, writing down this term is allowed. Okay, nothing but gets violated. Right? So it's a Lorentz invariant, it's real, it's bilinear, everything is good. The only criteria that this is violating is the fact that theory must respect some global symmetry as Coleman imposed. So if I also impose then the fact that my theory respects some U1 global symmetry under which U plus transform with the U1 phase, then I should not include this. Then I go back to massless theory. But by including this term, you learn one thing. Oh, I see. The way we can drop the mass term is if I impose some global U1 symmetry, or as we talked about, to gauge U1 symmetry. But there can be a role where I don't have to, insist on having such global symmetry. Then this term seems to be allowed. Indeed, there is a theory in the real world where we do have such a mass. If you have heard of what's known as the seesaw mechanism, that's the example, but don't worry about it if you don't know that example. But logically, this is allowed. And we can certainly talk about the massless theory by just dropping this term. But I'm explaining to you that instead of understanding this parameter to zero, without understanding why such parameter can be or should be zero, but now you understand in what case this must be zero, for instance. What is that? If I impose that this theory must be invariant under U1 global symmetry or gauge symmetry, then this term must be zero. So now I'm just giving you that there's a parameter, which is allowed in principle in connection to a symmetry. So this description includes the possibility of having massless bipolar. Okay, any other questions? Good. So that is the equations of motion. Now, for now, if it gets well, okay. So then I can do something on this. So for now, let's assume or take just to simplify the story. Let me take D star or D star to be zero. Okay, just to be simplified. Or I can say that I impose the C2 criteria where I do have a U1 global symmetry. Either is fine. So if I impose that, then obviously my equation of motion gets simplified just a little bit. Okay, I'm doing this because some of it seems to be unhappy or confused by the fact that I have this extra term. So let me just drop it. Now this equation can be massaged. So also let me drop the plus minus sign and I. It doesn't matter, right? Because something is equal to zero, so I can just drop this factor. So then let me write this out explicitly. That is equal to, remember, sigma bar was a 1 minus sigma. That gives me, oh, what is this? This, and then minus, okay, and then sigma Laplacian acting on U plus. Let me remind you, Laplacian is equal to derivative of I, like downstairs, not the upstairs. Okay, so that's the equation of motion. One useful thing to do with this is the following. So take this, and then I'm going to multiply sigma nu derivative nu. So I'm going to take that equation, multiply this factor. So then what happened is, so first let's collect this side. I get sigma nu, sigma bar mu, derivative nu, derivative mu. Once again, I can expand this into symmetric part and anti-symmetric part, right? But since this is already symmetric, I have to keep only the symmetric part from that extension. So let me keep only the symmetric part. And I told you that this is equal to 2 times metric, and then identity or delta in the scalar space. So if you do that, if you plug it in, that construction, what you get is the following. So 2 cancels 1 over 2. There's a metric which give you box, and then U plus is equal to 0. So what is this equation? In order to understand this equation, let's consider a plane wave solution. The plane wave solution says that I take this to be some prefactor, and then e to the either plus or minus I theta x. Okay, so plane wave with the coefficient function to be determined by actually solving the equations of motion. So if you plug back in here, what you get is that, because there's a box acting on the plane wave part, by the way, this is independent of the space and time. In other words, when I say plane wave, entire spatial dependence is controlled by this plane wave factor, right? And then there's the rest prefactor. If you plug in, what you get is p squared is equal to 0. Because if you take the dollar version acting on here, that's what you get. Okay, so far it's all math. Let's now extract the physics out of it. What have I achieved? Well, first I constructed Lagrangian. B, I derived the equations of motion, and I show that equations of motion takes actually the form that you have seen before. So that looks like mu. This doesn't look like mu at all. This is Klein-Gordon equation that you saw from the scalar field theory. So you might say, oh, this is a fermion. Why does it satisfy Klein-Gordon equation? But if you remember, I told you last time that doesn't matter what field in relativist quantum field theory. Every field appearing in quantum field theory, relativist quantum field theory, must satisfy Klein-Gordon equation. Because Klein-Gordon equation, as I just demonstrated here, is nothing but imposing it satisfies consistent dispersion relation for relativistic particle. So you should not be surprised. Well, first you should be surprised. And then second, you should say aha, because this is nothing but to say that whatever state described by this spinor field does satisfy the required criteria, which is to say that I'm describing now a massless state has some elicited state that I will describe now. Okay, so for now, that's what we learn from this. Is that clear so far? Once again, any quantum field at some point must satisfy Klein-Gordon equation. Okay, that's just a true statement regardless, because you can always take plane wave solution. There can be some complicated prefactor, doesn't matter. Eventually, it should be giving you this condition. Okay, good. So that's fun. Now, if you have included this term, on the other hand, I will not do it here. Maybe I can make it homework. You will see that in addition to this, something will appear. Okay, so if you have done it, I believe if you included the d terms, if I didn't set that to be 0, you will get something like plus is equal to, in this case, probably minus of that, maybe square, something like that here. Okay, so you learn that, certainly now if you again do the plane wave solution, you get some relation, something related to something like this. So you see, A, yes, the tilde takes the interpretation of a mass. B, from this sort of exercise, you can also fix what is the correct sort of sign you can put here as well. Although sign for the fermion doesn't take any physical status. So in principle, I think if I correct, I think you get this. Regardless whether you put the plus d tilde or minus d tilde, I think you get that. So from this, therefore, you understand that this takes the status of macro for the firm. Okay, but it's kind of firm mass. Again, the name random mass, which is allowed if you don't have a lower symmetry. Yes.
I think we're considering quantum field theory, so I think the equation of motion is one of the classical one.
That's right.
So why the quantum field has to be specified the equation of motion?
Good. So what I have done is I have not quantized the theory yet. So I'm still at the classical level. So I just took up something that that I know that I can write down consistent Lagrangian for spin half or helicity half, which I will show right after. And then I just studied the equations of motion, which again, as you said, corresponds to the study classical limit. And then once I understand everything and I understand everything is consistent, then I will quantize the theory. We will start talking about the quantum extensions, which are the particles. Any other questions? Yes.
Okay, you said that action should be real, but I think that would be not ordinary real number because it is constructed by Grassmannian numbers.
Yeah.
Okay, so then my question is how this section principle can apply because Grassmannian there is no something big and small in the Grassmannian number. So
There's no bigger and small in Grassmannian number.
Yeah.
So, okay, I haven't discussed it yet, but from the perspective of a path integral, we know how to deal with Grassmannian number. I mean, we can also deal with at the level of action too. There's a Grassmannian classical mechanics and all of that. Okay, I don't suggest you to look into that study. That it's not a fun and nothing actually useful. So we can all deal with that. But nevertheless, what you have to make sure is that if you write down something, and then if you pass on to the Hamiltonian, okay, everything goes Grassmannian, and quantize it, that should be Hermitian. So that's the ultimate criteria. Here, I'm sort of using S being real as the avatar of that property, which often works out. Okay? And you might say that, okay, so why don't we just go to the Hamiltonian and do blah, blah, blah. We will do it eventually. Although secretly, or even though it's not a secret, this theory has an important subtlety when you try to go from the Lagrangian to the Hamiltonian. Let me just say a word. Okay, so that you heard of that, but don't start with that. That subtlety is known as it's a Fermion theory is constrained system. It is what's known as second-class constraint, and you need to know how to deal with it in principle. But if you never learn that and you just do it without worrying about it, you got the right answer. So that's why most of the lectures for field theory for Fermion, they just teach that way. You get the right answer, and then or you spend 3 times more time just worrying about the first grade, the second-class constraint. Jesus, oh my God, you got the same answer. So in that sense, just do it. Okay, don't go into that rabbit hole. But ultimate criteria is you want to actually go and quantize Hamiltonian is Hermitian. So you get the unitary view. Okay, any other questions? Good. So now let's actually look at the solution to this plane wave equation. And that will teach us second information about that theory. So again, I'm going to take that equation as a motion now. I'm going back here because given the fact that I understood what's the meaning of this equation, I'm back here. And then obviously, for now, let me just write immediately because you get this if you look at the theory for U minus. Okay, so now let me try. This is once again some prefactor into the plus or minus p dot x, right? And by constructing Clay-Gordon equation, I show that system describes a massless state, right? What that means is that I can take for this p mu to be always the magnitude of the p, which let me just write it as p0, and then p vet. Is that clear? So energy of the massless particle is the same as length of the 3 vector. That's what I'm saying. Okay. So therefore, let me just rewrite this as let me just pull out the p0 component, and that's 1. And then let me just put text. Remember, this is the length of that thing. So if I scale out, the only length of information is the direction of that vector. Okay. And then momentarily, since I will use the lower index p mu, that's obviously 1 minus Compasson p, right? So I lower the index by metric. Okay, so now I'm ready. So let me just plug back in and read off what do I get. So this equation turns into, so if I first take a derivative acting on the temporal part, I get plus minus p0. That's 1. And then remember, this is a lower index which means that it's the derivative with respect to upper index spatial vector. Yes? Good. So then if I look at this, I can look at that as lower index p mu and upper index x of mu. So that I can just nominally do the derivative. But I told you that in that basis, I have minus sign in front. So if I do the derivative, I will combine that minus with that minus. I get the plus sign. So I get a sigma dot p hat acting on up, which is the prefactor. This function is equal to. That is the equation of motion. So what is the game plan? So given the equations of motion, I wanted to get a solution to the equations of motion. And then I'm using the ansatz, which is a plane wave ansatz, and then reduced down to this equation. And this is the equation for UP, right? This is, if you like, eigenvector equation. So that's good?
Professor,
Yes.
if you just write P upper indexes, then you will get the inverse sign in that?
Well, then you have to be careful on that. Yes, careful in the sense. This equation is written in basis where x is with upper index. If you want to insist on using p upper in mu, then this is a lower, so then you have to lower here, which we get minus m here. There's always compensating. This is answer no matter what you do.
Thank you.
Okay, so what does that tell us? Okay, let's consider the case where p0 is not equal to 0. Are you happy with that? Okay. You can ask what happens if p goes to 0. Well, that's empty. Nothing's there. So we'll love with that. So let me rewrite this equation as follows. P hat sigma acting on the UP, let me divide it by 2. Then the 1 gives me minus 1 over 1/2 UP. Okay, so it looks like there's an operator acting on this function with the eigenvalue minus half this equation. So what is that? So recall, when we studied Fermion system, which the rotation generator, which was this, in this case, it's actually 1 over 2 times the sigma matrices. So that what that shows, therefore, is that this equation nothing but measuring a angular momentum, internal angular momentum, so you can call it a spin, along the direction of propagation. And this guy picks out the unique eigenvalue under that value, which is minus half. So, and that particular combination, meaning angular momentum or spin, along the direction of propagation is called the helicity. Therefore, we learned that this U plus guy has helicity, which I call H minus H. And yes.
So can you repeat the explanation of the helicity?
Okay, helicity, yes. Let me explain that. So helicity is, if you like, a spin along the direction of a propagation. That is the helicity.
The definition.
That is the definition of helicity. Okay, and in this case, there was no quite a separate meaning of a spin itself. It is only this guy that picks out, which can, in principle, we can have a deeper discussion. Okay, so for massless particle, it is the helicity that is meaningful, not the spin itself. Okay, and what we have shown here is that U plus guy with a maximally confusing notation now has a minus half helicity. And I warned you last time, remember that. And if you repeat the same thing, the only difference is that now there is this minus sign there, you will find that you'll eventually get this equation, for minus guy, which is a terrible choice, has a 1 plus half guy. So we learned that, what is that? Okay, so we say that a state with a minus helicity half is called the left-handed Fermion, and the one with a plus half we call right-handed Fermion. And so I'll give you a little bit more word about helicity. But now let's first, before that, let me summarize what we have found. So construction done. We found, okay, they want to describe a massless particle. And it should be something to do with the spin half sort of thing, right? Because that was exactly how we constructed it. Because we studied half, zero, or zero half representations. So some way it should be associated with the spin half state. And then statement I just made gets a precise by actually studying this equations of motion in the plane wave form. That actually what we learned is it's not just a spin, but actually it's a helicity taking either plus or minus half. Okay, so that's what we learned. Now let me say just one more thing about the helicity. So you might say, okay, is it spin or not, right? Tell me, is that a spin or not? Because I say a spin along the direction of propagation. If so, then why don't we just talk about the spin? Okay, the reason is there isn't such a thing for massless particle, and it is actually easy to start thinking about it, although to complete the thinking takes some time. So for massive particle, which means p squared is equal to m squared, then okay, here is the line momenta. But for massless particle, you can always boost this guy, go to what is known as a reference or standard, whatever, momentum, in such a way that you go to the rest frame, meaning, you have a zero momentum and then energy becomes mass of itself. Okay? So if you go to that frame, then you ask, what are the all possible symmetry that leaves this standard or reference momentum invariant? What that means is that I'm going to see then in that frame and then ask what are the meaningful quantum numbers that I can talk about. And obviously, every rotation that acts on only this part, which does not touch this part, is invariant because this is zero component. So therefore, you can see that there's SO3 rotation acting on here, but we learned that probably the proper way of thinking about it is SU2 acting on there, and that is nothing but spin. So for massive particle, yes, we can talk about spin. Okay, we can talk about +1, 0, -1, all of them. For instance, in the case of the spin 1 particle. Now let's talk about the massless particle. The massless particle, best we can do is go to this frame, E 0, 0, E. I mean, I'm just picking a specific direction, but you know what I'm talking about. I'm basically talking about this. Okay. Now you can also ask yourself, okay, now I'm taking this as my spatial or reference momentum. You can ask yourself now, what is the immediate quantum number I can talk about if I go to that frame? Which means that what are the symmetry Lorentz transformation that leaves this momentum invariant? Obviously, you don't want to talk about something that mixes up these two guys because it's going to change it to something else, right? You can reshuffle this stuff. But obviously, anything that acts only on these two components will leave this momentum invariant. Okay? And who are they? So they basically act on the x and y plane with the z direction fixed by this. That's literally just the U1 rotation we can talk about. So for massless particle, what you have is actually just U1 phase, a single U1 phase, not entire spin degree of freedom that we talk about. And so that U1 phase is nothing but this. So if you had arbitrary freedom to talk about entire rotation, you can talk about entire spin. But in the case of massless particle, I'm telling you that this is the maximum you can talk about. In fact, this would just collapse into a uniquely direction of momentum with possible some angle variable. Okay, so now this is not a full 3-dimensional rotation we're talking about. Well, a particular direction rotation picks up, and there's only U1 phase, not the entire SU2 phase, and that is a helicity. Okay.
The main point is that for the massless particle, we cannot define the spin, but we can only define the helicity.
Yes, yes, that's the only meaningful quantum number for massless particle. And there are a group of people, like people who are actually doing active research now, may say, "Oh, that's not quite totally true." So So should I go on this direction or not? So if you read the Weinberg chapter 2, okay, you can ask, what is the maximal, Lorentz symmetry, the axiom here? And then I said, oh, is it axiom 2, which is U1, therefore there's the U1 phase, which is obviously that's what I'm talking. But if you are doing slightly carefully, you actually get Euclidean two-dimensional symmetry, which is to say that you just as if living in a two-dimensional Euclidean world. Then there are not only, in addition to the rotation along the plane, perpendicular to the plane, you can also move around the two-dimensional. For two-dimensional translation here, and in addition to the quantized value, here we talk about either plus half, minus half. Euclidean two-dimension include not only U1 rotation, but also two-dimensional translation. Then this gives you continuum eigenvalue. So there's an ongoing research program called the continuum spin state. And that's exactly that. And if you read Weinberg already, he talks about it. And his justification is that if we look at the photon, obviously we don't see continuum degree of freedom. We only see up and down, right? So we're gonna set the eigenvalue associated with the translation to be 0. And so we constrain ourselves to only U1 part, and then we just stick to the holistic. But then there are theorists, good theorists, still exploring whether this full can be realized, and there can be any meaningful observation we can make. Sorry. I never planned on this talking about this, but anyway, it happened to be. So it looks like you guys are maximally interested only in this part, not the rest of it. Anyway, yes.
Is there no SO2 in time and direction of P?
Here, but you're gonna mix up, so that will not leave the standard momentum invariant.
No, E and E.
Oh,
Speed of light.
I understood that word. I cannot understand how that this looks like. Okay, thank you. They were saying, what if I acting on here? But let me see. I think, does that leave this invariant? So really the criteria is that take a Lorentz transformation that leaves P invariant. And you can check if you do boost along this regression, you can check whether that's the same. I'll think no, because it's a simple to understand. Wait, is it same? I think it's no, because if you boost, then you certainly increase the momentum along the direction. But for massless particle, you have to also increase the energy simultaneously. So basically, you will keep the form of the P mu, but you will increase the component if you do the boost along it. Right? You just accelerate a little bit. But you can check. So you have two homework now. Right? Tensor versus product and this. I will not forget. Okay. Okay, we can move on. Any other questions? Very good. Okay, so that's all good. So what have we learned? So therefore, we learned the following. So there is this guy, but Lagrangian for U plus, so that we can nicely write it as this. So let me drop for the moment the last term. At least I mentioned to you. So then we have this. Okay. So if we keep only one of them, just making sure if I'm missing any content that I want to talk about, instead of a long discussion about this. All good. Okay, good. So indeed, I can do one thing very quickly. So let's look at this equation again. So here, let's pick a specific direction just to learn a little bit more about this function. Because at this point, we learned the properties of that function, but we haven't actually constructed the explicit form of it, right? We can do it arbitrarily, but let's do it easy one. So let's pick this direction to be z direction. Okay? So then my equation collapses to 1 plus sigma z acting on IM function is equal to 0, right? And since this guy has a 1 minus 1, if you do it, this is, oops, 0, 0 to epsilon u. And you can find two component vector that satisfy this equation easily, right? So one solution obviously can be something that has 0 in here and then 1 downstairs. Right? Good. And so that's the, for instance, UP for plus, U plus, and then you can do the same thing for, so here, let me just write there for, in the case of z direction, it looks like here, okay, if I pick p hat to be z direction, and then for u minus, this will therefore appear to be 1, 0. So upstairs, up component, that's a plus half velocity, down component, that's minus half velocity. So these are two eigenvectors. Okay, spanning distance. Okay, now I'm gonna move on to here. I will now construct the Dirac Lagrange for the Dirac fermion. So we have all the gradients. So now let's impose. So in addition to C1 to C5 that we talked about, let's impose parity. So then we have to understand what parity does. So we already saw that parity does the following. Okay, saw that. So which means that in terms of U fields, I can say that given a U plus and X and T, parity will send that guy to be U minus at minus X space. But once again, we talked about the fact that if there's a version of parity, I can always compose that with a possible U1 phase rotation to talk about different version of parity transformation. So to be more general, which I will make use of this freedom soon, then let's define the parity transformation actually on U plus to be this one. Okay, so this must make sense, but I'm saying there's this arbitrary possible phase ambiguity, which we will fix. So the similar token, let's say that the parity acting on the U minus field with some other possible phase, but descending to U plus, but at the parity inverted space point. Okay, so that's one thing that we can immediately observe or know. And second, in order to construct the parity invariant theory, now we can also understand that the gradient goes to minus gradient under the parity operation because X flips. That's clear to see. Okay, now with these two facts understood, now I will construct a theory, possibly general theory, again quadratic. Let's remember C1, Lagrange is Lorentz invariant. C2, there's internal symmetry. C3, it is a bilinear, so that we get linear equations of motion, right? C4 over C4.
No more true hyperbola.
Very good. So we talked about one derivative theory, so let's just talk about only single derivative theory. And C5, real action, okay? And sixth condition is that I'm imposing parity invariance. So now let's recall very quickly, if you had a U plus or U minus, the building blocks were this, or you construct this guy, or there's an antisymmetric tensor, right? We talked about it. But we didn't use antisymmetric tensor because it looks like the only way they can enter in the construction of Lagrangian is if we talk about not just by linear action, but you have a form here, which we're not doing for now. Okay? So same thing with the minus. Oh, that doesn't. So we can start to do this. Okay, now since we have both of them, not just one of them, you can ask yourself, are there extra Lorentz tensor vector scalar we can construct? Right? Remember, what we are doing is, now if I'm given both of them, and then I'm gonna write down the most general action Lagrange consistent with the C1 to the C6. So what are the extra ingredient or building block I have? Because I have extra field. Well, first of all, I can talk about this or that. Right? This must be Lorentz invariant. Is that clear? Clear? This is like, remember, this schematically in big fonts behaves like a U minus, right? Behaves like U minus because I'm only concerned about Lorentz transformation property. Then, this is as if U minus square, which we knew that we can have that as a Lorentz invariant object. That's basically that. We have that. And then what else? In principle, one can try to have something like this, but written in that form, or the other way around, something like that. Okay. So therefore, Lagrangian can have the following terms. So first of all, I already know a lot of terms. So let's keep this. So I have that. I have that. What's the best way of writing? So instead of actually writing with equality, because I have to impose parity, let me just list possible ingredient. So I can have derivative of b mu, which I mean u plus stagger sigma bar. Yes. And then I can have a derivative of w, right? By which I mean, you know what I mean. U. That. But also I can have u minus stagger u plus stagger u minus. Also, in principle, one can write down something like u minus sigma dagger, sigma bar, or the other way around, right? Something like that is allowed. Okay. Now, I will include this and that, and that and that, but I'm not going to include this guy for a moment. Like for a moment, I mean never in this course. You might say, why? Because I'm trying to be systematic. And why am I saying that? A, Coleman doesn't talk about it. But B, better way of saying it is, this sort of term is known as a kinetic mixing. Okay? So there's two fields I want to propagate, but this describes, I was trying to propagate, but some weird guy pops out of me and then continue. Then I compete again, it pops out of the other guy and continue. So they mix along the propagation. And there's always, you can diagonalize things such that you don't have kinetic mixing. And then you can only talk about diagonalize the kinetic term with extra interactions. Okay? So with that understanding, so I'm not going to just talk about kinetic mixing.
It's the kind of the plot that you might not different particle than the kinetic mixing of something. Approximately some kind of
Sorry, say it again.
If the U plus and U minus are different kind of particle than
They are different kind of particles indeed.
in the not only the chirality, like some of the
But then by then they cannot mix.
they cannot mix.
What, so when you can write down something like that, that means as a quantum state, the state created by this guy must have the same, not only Lorentz property, Lorentz transformation property, but it also must have the same other quantum numbers. So otherwise the 2-point function is 0. Does that make sense? All right, so basically you're trying to say that, oh, I want to look at the state overlap between the guy produced by that guy and the guy produced by that guy. Okay, when that is non-zero, as if I can write that mixing, these two states must have all the same quantum numbers. Yes. Okay, so therefore I'm not gonna talk about this. Once again, you can always go to the basis where you can just talk about this by proper basis rotation. Yes.
Can you understand neutrino oscillation from kinetic machine?
Can I understand neutrino oscillation from the kinetic mixing? I don't. Do you?
I think it is similar because neutrino, some flavor of neutrino was going and somewhat strange one is coming.
Yeah, so good. So usually, I'm not saying this is the only way. But usually, you first diagonalize the kinetic term. Remember, this is the base for the cause quantization. And if you start having a mixing given at the base level, then okay, how you think about the quantization. So first you find that because then fluctuation of that guy have non-trivial commutation relation of that guy, all that kind of complications. So usually you first diagonalizing. Then once you do that, then you have a non-trivial mass mixing here, and then you therefore describe all the neutrino oscillation in terms of a mass mixing. Another question. Yes.
Why the kinetic mixing of the KAIST equation is allowed for the kind of?
It is allowed, and you can also diagonalize it.
I don't know.
So yes, there's a dark photon, there's a kinetic mixing, and then one basis of dealing with that is to diagonalize that kinetic term. But then you have dark charge coupled to us, or our charge coupled to dark photon, so you can go to that basis.
Then the effects are in any way.
Yeah, the effects remains.
So the same phenomenon can be appears in the element.
So I'm not saying that theory, say I have these two and the kinetic mixing is equivalent to a theory with only that term. So there can be a physical implications or effects in principle, just like that photon. So I'm not saying they are not physical. All I'm saying is that there is a description where the one with this, the one without this, but whose effect is translated into some other terms, which I will talk about. That's what I mean. Okay, good. All right, so okay. So that means I can finish writing down the Lagrangian, and then we will be done with it. So let's come back to here. Now I'm going to impose the parity. So because of this fact, and by the way, this is constant phase. Okay, so these are the constant phase. So then, if I call this to be, L plus, okay, by which I mean plus minus I here, plus minus I here. This is my L minus. Then you see that the parity flips these two. So this guy goes to that under the parity. Even with arbitrary phase, because arbitrary phase cancels out because you have a one U dagger, so they cancels out. Okay, so therefore, in order to have a parity invariant part that has this term, at the very least you have to include both. So therefore, now Iraq is called, and you have both plus minus. You have to have L minus L plus simultaneously. Okay, under the parity, they have to have. You should be have both. That's why if we only look at the theory with only one chirality or helicity, that's not parity invariant. What about this term? So in order to study the parity invariance of that term, now let me write as follows. So I'm just going to write this in the Hermitian function, which is this. So this is already parity invariant. Good. So now let's worry about the parity invariance of this mass terms. In order to do that, let's just look at how this transforms the parity. And here I'm taking M to be, in general, complex number. So M can have its magnitude and no infinity. So it can be, in general, a complex number. Understanding complex phase structure of the fermion mass are very important subject, by the way, in physics, because that captures CP violation. If you have heard about axion and blah, blah, all related to this sort of discussion. Anyway, so we are not there yet, but anyway, let's understand how parity acts on this. So that gives me, let me just write it this way, M plus M star goes to, under the parity, M so and then let me rewrite this in a suggestive way. Okay, so let me rewrite so that, because I wanted to see what's the sense that this can turn into the same format, right? So that's why I'm imposing parity invariance. So in front of U minus dagger U plus, that's the M star. So I want to rewrite first in terms of U star, sorry, M star, and that gives me okay, 2 alpha plus I2 minus I1 M star, okay, plus permission conjugate, or plus conjugate. Then we can split it. Okay, so that's my play. So what have I done? I took this, I just performed the parity transformation according to the thing that I said, and then I just rewrote in a way that each of the term takes the same form as in the original action. Okay, that's what I have. Good. Now I can make a precise statement. Oh no, I did the same. Sounds good. Okay, so now for any given arbitrary parameter m, because I want to have a parity invariant theory for any parameter m for now, which means that I'm gonna take any arbitrary phase alpha, right? Then the question is, do I have all version of a definition of the parity transformation that leaves this term invariant? That is the question I'm asking. Is that clear? Remember, the definition of the parity is not unique. It's not unique, right? You have a continuously many different kind of definition. The only question is there a definition of P that leaves this action invariant? The answer is yes, because I can just take what? Like phi1 minus phi2 equal to alpha. For any alpha, I can only choose phi or phi2. This is true. Then under that definition of parity, this action is invariant. Okay. There's a second way of saying it, which is what Coleman said. So let me also repeat that thing. I'm slightly worried if I say that also, whether it confuses you or it clarifies things. But nevertheless, let me try. Another way of saying it is the following. So, okay, I start out with a theory with a complex parameter m. Now, step number one, we are gonna make a field redefinition in a way that I'm just gonna rescale my U1 field, U plus field, to be U plus, so e to the I alpha U plus. Okay, so I just made a field redefinition through this U phase rotations. If you do so, then you see that, because there's a dagger, because it was dagger, so it cancels out the phase here, the same thing happens here too. Yes? So then, after this, I'm left with, in terms of a new field, okay, I have a real parameter, theory, like so. Okay? Then I make a parity transformation. So then under the parity, because this is a real parameter, this is scaled out, I can take it out of the thing, I get phi2 minus phi1. And then phi1 minus phi2. Imposing the fact that this should be the same as before, obviously you can see that then I can choose phi1 equal to phi2 transformation. So under the parity, you plus and minus transform the same way, basically. In particular, I can choose this to be 0. Once again, there are many different ways of defining my Fourier transformation. It doesn't matter. So I can just say that plus or minus x comma t that goes to plus minus plus everything inverted points. Okay, so this is what Coleman said. There's one reason I didn't say, well, I said it. Thank you. But one of the reasons I sort of reluctant to do that, which is correct statement at this level, but whenever your fermion is also charged under vector field, which we will discuss, then this is quantum mechanically is not just a good user definition. There's what's known as anomaly that you have to be more worried about both of those. That's why I presented it that way. Okay. Anyway, so that's all for today. No lecture. Next week we will meet the week after. Yeah. 예.
있으니까 미치는 없잖아요.
네.
근데 사실 이게 약간 뭐라는 이걸 얘기냐면 이제